Hey guys, welcome back to another ARIA SK Maths tutorial or video, and in this video I'm going to be talking about how you can use integration to find the exact length of curves, such as this one you see on the left. This is actually y equals x squared, and I'm going to be showing you guys how you can use integration to find the exact length of this purple region which has been shaded. So I'll be showing you guys how you actually derive this, and yeah, then I'll be actually evaluating it. So here in our case, we have a region which is bounded by x equals 1 and x equals 3. So basically you want to find the length of this curve between x equals 1 and 3, like so. So before we do that, I'm going to show you guys how we can actually create a general formula to get the length of any curve in any bounds. So let's draw my random curve. Let's just call this f of x. So this is our curve y equals f of x. And let's say you were asked to find the length of this point, like so. So what we can do is we can actually I'm going to draw a bigger version of this over here. And let's just say it's over this, like this. So this is our purple region, and we want to find the length of this. So the way we can do this is similar to integrating normally, where you'd split this into a bunch of rectangles like so and find the area of each one. We're going to split this into a bunch of triangles. So usually these rectangles would have width dx. So we're going to use the same sort of thing, and we're just going to split this curve into a bunch of triangles like this with base length dx, like this. So what this allows us to do is we can just work out the length of each of these hypotenuses, and if we make dx really small, then it's going to become exact. So now let me enlarge this again, just so you can understand this even clearer. So we've got our curve, and we've got our triangles, like so. So this is just one of the tiny triangles along the curve. So if we call this length dx, then let's just call this first point x, like so. So now this point over here, well, we know at this point the y coordinate is just going to be f of x, right? So at this point, the y coordinate is actually going to be f of x plus dx, because we're going to be at this point now. So the y coordinate has increased. So what that means is we can actually, I'm going to draw another triangle to make it a bit more clear. So this is the triangle we're working with now. We have a base of dx, and if we want to find the length of this, well, this is just going to be f of x plus dx minus f of x, like so. And now what we can do is we're trying to find this length, like this. So knowing Pythagoras, we can just work out that length to be, we'll just call the length L. We know L is going to be the square root of dx squared plus this squared. So I'm just going to write this like so, f of x plus dx minus f of x. And we'll just put that in brackets. So that might be looking a bit confusing now, but there's also another way we can think about this. So if you've watched the previous short, you'll know that you can also write this length as simply dy, because the change in x and this is the change in y, and overall this is going to be the gradient dy by dx, like so. So that means we can rewrite our length formula like this, a lot simpler. We can just say it's the square root of dx squared plus dy squared, like so. So that makes it a lot more simple. And now I'm going to be showing you guys how we can actually apply this to our original question over here. So we have the curve y equals x squared, and we want to find the exact length. So what we can do is if I redraw y equals x squared, and we are looking in this region like so, I'll just mark it out with red. So we've got x equals 1 and x equals 3. Let's first split it into our triangles. So I'll just draw a random triangle over here. And we're going to pretend this length here is dx, this one. And we know this is also going to be a corresponding dy. And now what we can do is we've got this equation. All we have to do is differentiate on both sides to get dy is equal to 2x dx. And now you can see we've literally just got our dy and we can just leave dx like it is. So that means our L over here is just going to be the square root of dx squared plus dy squared, which is the square root of dx squared plus 2x dx squared, like so. So there's our length. We've worked out the length of one of these tiny triangles, but we want to work out the length of all of them combined so we can work out the total arc length of that curve. Well, luckily for us, we actually have a handy trick for working out large sums or infinite sums, and it is in fact the integral. So if you might remember, the integral is just equivalent to, well, not really equivalent, but it's just sort of sum to infinity. So we're going to be summing up an infinite amount of these tiny triangles. So all we really have to do is we just have to take the integral of all these L's, and that will come out to be this, the integral of root dx squared. I'm going to expand this bracket out, so we're going to get dx squared plus 4x squared dx squared, like so. Now we also can't forget our bounds, but luckily these are already given to us. Nice and easy, we just get 1, 3, like so. So lower bound is x equals 1 and upper bound is x equals 3. And from here, we're just left with an integral. So I will just write this out and then we can just evaluate this. So this is the integral we're working with to just solve for this length, like so. We're going from 1 to 3 of the square root of dx squared plus 4x squared dx squared. So now it really just comes down to evaluating this integral. The first thing you might notice is that there's not actually a dx on the side, which is why we've got the two dx's inside the square root. So we need to get those out, and we can do that pretty easily by just factorizing. So we can split this into a dx squared multiplied by this, 1 plus 4x squared. And then you can see we can just write this like this. Actually, I'll just do it over here. So 1 to 3 of 1 plus 4x squared dx. So you'll be left with this integral, and this integral is it's a standard integral, but it is at the same time pretty difficult. So I'm not going to go through actually solving it, but I'll just explain the steps in case you do want to actually try it. So the first thing you'll notice is that there's actually there's a compound term within the square root. So you can use a trig sub to get rid of that. And what you would substitute is you do something like x is equal to 1/2 tan u, so that when you put it into that x squared, it becomes 1/4, and then it cancels out the 4, so you're just left with 1 plus tan squared u. And then you can use the identity 1 plus tan squared u is identical to secant squared. So you'll be left with secant squared inside the square root, and that will just cancel down to secant u. And of course, you also need to consider out the dx. So just work out dx like so, 1/2 secant squared u du. And when you combine these two, this will just turn into a secant squared. So this entire thing will go into secant u, and this will go secant squared du. So you'll overall be left with something like 1/2 squared u du. And from there, you just have to solve that integral. Takes quite a while because you do need to first of all split it up into secant squared multiplied by secant u. I've said it the other way around, but you know what I mean. And then you can split that up using integration by parts into just you just do secant tan u and just tan, so you'd end up with by parts, and then you just solve it from there. So you can see there's a lot of steps, but this is the basic idea. And once you solve that integral, you should approximately get something like 8.268. So here we go. This is our approximation. Obviously, if you solve this integral, you'd get the exact value for the arc length, but this is an approximation for the arc length of y equals x squared from x equals 1 to x equals 3. So we can actually generalize this, and we can actually generalize this to any curve. So let's just draw out some random curve. Let's just have another f of x. Let's have this. And let's say you wanted to work out the arc length from x equals a to x equals b, like so. So what we can do is we can use our triangle splitting method. Just going to draw out a general triangle here. So we have dx and we have dy, and this arc length is going to be the square root of dx squared plus dy squared, of course. And usually your function is actually given in the form y equals f of x. So when this happens, it's really easy to find dy, because dy is just going to be equal to the derivative of f of x. So we can actually use this to create a generalized function, which is going to be in this form. So we have dx still on the base, but on the for the height, we can just write this as the derivative of x. And then, of course, if we put this into here, I'll just do this all in one step. But if you put the derivative of x of f squared into here, then we can factorize out the dx, and then its square root is going to cancel out with the square. So we're just going to get this length as 1 plus f dash of x squared multiplied by dx. So therefore, we can generalize our arc length formula to simply become the integral from a to b, since it's always going to be from these x values, of the square root of 1 plus f dash of x squared dx. And you can see this is actually the integral which we had to deal with over here. If we go back to this, so this is 4x squared, which is, if we go back over to here, so our function was y equals x squared. When you take derivative, that's 2x, and then when you square that, that is 4x squared. So that's what we had to deal with over there. And yeah, this works pretty well. One drawback to this is that you're always going to have to solve an integral with a square root in it, and these can usually be pretty difficult, especially when it's not a polynomial and you can't just do a u sub. It can be pretty difficult. So for example, if you want to find the arc length of y equals sine of x, you're going to be left with an integral 1 plus cosine squared of x, and that is a pretty difficult integral. I don't even think it has a real solution. But yeah, so here's the arc length formula. Hopefully you learned something today, and yeah, that was answering our original question of finding the exact length of this purple curve. Thanks for watching, and I'll see you guys in a future tutorial. Bye!